Hello everyone, my name is Kübra Alemdar and today I am here to present our paper RFClock, Timing, Phase and Frequency Synchronization for Distributed Wireless Networks. So in this picture, you can see a aerial view of Boston City, which I'm coming from. And this city has been served by many different kind of wireless network and system, which are very important infrastructure for our daily lives. And this system can support different type of applications like smart homes, Internet of Things, and industrial application, and many others. However, this network architectures is going under a radical transformation when especially we are transitioning from 4G to 5G and also 6G. And we believe that distributed wireless networks play a key role in this transformation. However, these networks has a common point that they need to overcome some fine-grained synchronization challenges in order to realize their full potential. And first challenge is that carrier frequency synchronization. Any wireless radio forming a link with another radio generates its carrier frequency from its local oscillator. And we know that this local oscillator has slightly different frequency than expected carrier. Therefore, there will be some carrier frequency offset between these radios. And to show that this effect, we simply sent a BPSK modulated signal over these radios. And on this constellation diagram, you can see the phase of these IQ samples will rotate over the time, and which is due to this effect. And second challenge is that time synchronization, and multiple transmitters need to align their transmission at per symbol level basis. In other words, these radios need to coordinate their transmission time. And in order to investigate this effect, we use a distributed beamforming setup, which two transmitters and one receiver. And we know that these radios used a timing signal, 1 PPS, to coordinate their internal events. Therefore, we fed these radios with the 1 PPS signal with a timing offset. And at the end, what we observe is that in this figure, correlation inaccuracy of between this cross correlation peak from these two radios is more than 14 milliseconds, which yields an error in channel estimation, and eventually it will cause an incoherent beamforming. But if we have PPS alignment with these radios, then we can resolve this issue where you can see on this figure the correlation peaks get aligned in 1 microsecond level symbol time. And the last challenge is the carrier phase synchronization. If we assume that these radios simply send a single carrier frequency, which will have a carrier frequency offset, and it will have a random initial phase, which will be different and random for each radio. And at the receiver, each transmitting signal will experience a phase rotation, and they will sum up. Eventually, they will sum up in phase if we compensate these errors, or otherwise they will be out of phase and resulting destructive superposition, which will attenuate the signal. So in order to see this effect, we just sent a unmodulated sine wave from one transmitter to 3 receiver, which are replaced in a static environment. And as you can see from this figure, if there is no synchronization, we will see a phase rotation over the time. But if we use a shared clock, then we will eliminate this phase rotation, and at the end, this transmitter receiver pair will have only constant phase offsets. So to address these challenges, we propose RFClock, which is an over-the-air synchronization platform that achieves both frequency and time references without modifying any physical and link layer protocol. And in this picture, you see our prototype, which includes different design elements, which I will get in briefly. But before that, if we look into RFClock network architecture, RFClock can be integrated in any SDR radios, and it provides 10 megahertz and 1 PPS signal. And also its system has a leader-follower architecture where leader generates a type reference signal which is distributed to all followers. And these followers can synchronize their signal according to this reference among themselves. Right now, if we go into the design steps of the RFClock, our key idea is simply by that combining two-tone signal, which are separated by reference clock frequency, we can generate a quadrature signal oscillating with this average of the two tones. And the difference of these two tones also act as a modulator to control the envelope of this resulting wave. When this combined signal passes through envelope detection, then it will extract this. It will extract a sine wave. It will be at the desired clock reference frequency. However, since we don't use any linear noise amplifier or all elements are passive, at the end, this signal might not be strong enough for the radios to detect it as an external clock. Therefore, we redesign our envelope detector with the 4-stage Dixon rectifier, which is optimized to leader frequency to obtain a maximum possible power. And also, RFClock can be impacted by the interfering RF signal. To mitigate this, we design a tunable matching filter that allow RFClock to switch its frequency band. And simply this matching filter consists of some tunable capacitor bank, which are very ultra low power and can be adjusted digitally. And we design our matching filter, which is optimized to 3 different ISM band, which these frequencies are complying with standards. If we put design components in design components all together, if we go over it, first our leader generate a combined signal over the air, and this signal passes through the first stage of this circuit, and our adjustable impedance matching filter is optimized to this leader frequency. And from this plot, you can see our combined signal rectified with the Dixon rectifier and with DC offset. And in the second stage, we use an envelope filter to get the envelope of this signal, and we remove the DC offset with AC coupling. However, because we use nonlinear devices in our envelope detection, there will be some harmonics that will degrade the RFClock performance. That's why we filter these harmonics with the bandpass filter. At the end, we extract the clock signal at 10 megahertz frequency, which will be synchronized among all followers. And in the second step, we design our system for time and phase synchronization. But in here, the first issue is that we know that when there is no synchronization, there will be clock drift between radios, and then they will be drift apart from each other. But with RFClock, we can eliminate this drift, but still we will have a phase offset between this clock we need to eliminate. And the second issue is that when we generate a timing signal from this extracted clock, also there will be a timing offset between these PPS signals. So our goal is to align these clock edges and also PPS signal among followers to obtain time and phase synchronization. So to achieve these goals, first we extract a PPS signal from our extracted clock frequency. And now we are aware that there will be a timing offset with PPS, and also there will be a phase offset between clock edges. To calculate this phase and timings offset, we use a UWB radio because it has very precise time stamping feature. And with the UW-based message protocols, our follower and leader can exchange messages, and at the end, follower gets estimate of this timing offset. And it will reset its local PPS based on this timing offset, and still there will be a residual phase offset because of the clock edges. And this also phase offset will be eliminated by daisy chain of delay models in the system to align them. And in this section, I will explain our evaluation method and results. So on the left side, you see our indoor setting. Our experiments are performed in indoor with a crowded office environment, and also outdoor with loss and unloss conditions. And we simply send a Wi-Fi signal which consists of a legacy training preambles. By using this preamble, we estimate the CFO between these two radios. And we compare different synchronization platform like our platform, and the second one is a wired solution which will be RFClock, and the other one is a wireless solution GPS Duo in outdoor settings. So our first performance comparison is that we compare all these synchronization platforms, and from this result we can understand RFClock performance is superior to GPS Duo, and its performance approaches the wire solution RFClock. And we also tested our system in different channel conditions. On the left side, it shows RFClock performance in indoor and outdoor loss and unloss conditions. And we can say that RFClock is not significantly impacted by unloss condition indoors, and slightly degrades outdoors while maintaining CFO within permissible range. And on the right side, we test the performance of GPS Duo, and when GPS Duo lost its signal from the satellites, this clock starts drifting from each other, and it will result in increased CFO error. And the second evaluation is based on testing our time and phase synchronization. And we use time arrival of estimation by using UWB radios. When meeting a UWB radio sending a signal to a receiver, the receiver will extract a channel impulse response. And we know that direct path of this signal will be our time arrival of time. So therefore, if we extract the first path of this channel impulse response, we can estimate the time of flight of the channel. So by using this method, we compare RFClock and RFClock performance, which shows that they are in the picosecond. Their error in time of flight measurement is picosecond level, and it's nearly equal to RFClock. And also on the right side, you can see that distance versus RFClock performance in terms of the time of flight error. And this shows that degradation start after the 150 feet, which is our RFClock coverage, basically. And also we tested our system for how phase offset estimation happening. And in this figure, you can see that we estimated our phase offset in different channel condition. First one shows that our channel condition is outdoor, where radios outdoor and in loss, and we can detect first path of the signal. And the second one is in the rich multipath environment in indoor, and we still be able to detect the first path. And the third one is in the unloss environment, and from these three figures, we understand that our error in phase offset estimation is less than 5 milliseconds. But in the last condition where our radios in unloss environment, but there is an obstacle between them, our algorithm is not able to detect the first path correctly. So we adjust this algorithm by dynamically changing the noise threshold in the radio, and eventually it detects the first path correctly. So this will reduce our phase offset error estimation is from 7 nanosecond and 5 nanosecond. And finally, to enable a distributed coordinated beamforming, we design an experiment with four transmitters and one receiver. Each transmitter sends a frame that consists of a unique gold sequences and with the same OFDM payload. And we tested this setup with 6 different modulation schemes. And our results shows that RFClock performance is close to octoclock until the 16 QM, and after 32 and 64 QM, its performance slightly degrading, and also GPSTO doing worse in comparison. If I conclude that RFClock is designed to operate in generalized environment as a standalone unit, and it is suitable for more SDR radios in today, and its performance is close to current wired synchronization approaches, such as wired solution as OptoClock, and performs better than the state-of-the-art GPSTO. And it supports emerge application with its performance is mean of its CFO offset under 0.1 Hertz, and it is time phase alignment is less than 5 nanoseconds. And if I give an example here as an emerge applications, the requirement for 8.11 AX and AC to achieve multi-user MIMO, the relative clock offset should be less than 350 Hertz, and transmitter should be in less than 400 nanosecond timing constraints. And for the requirement for realizing MIMO with transmitter diversity in 5G should be less than 65 nanoseconds. Thank you for listening.